welcome. Let me ask you first a question. How many of you are using Kafka? Jesus Christ. We have expert audience. Any event-driven architecture? Okay, nice. So, welcome to streaming platforms in event-driven architectures. My name is Leandro Damascena. I'm Senior Solutions Architect at AWS. I'm joined by my colleague Stefan, that also is Solutions Architect at AWS. And today we'll talk about the common patterns that you have when building event-driven platform. Of course, there is pitfall, there is challenges, and there is some performance topics that you need to cover here. We expect that you leave the room, you walk away from this room with enough knowledge or some benefits from implementing an event-driven architecture. But before I talk about event-driven architecture, let's cover some important aspects, how the world evolved until you get here. 20, 30 years ago, 4 years ago, I see some faces here that can identify yourself with that. We are building monolith. And monolith is amazing, because monolith is everything in one place. Monolith, just let me start the time here, just not forget, sorry. Oh, sorry. Where is my mouse here? Jesus, you can count, put in your mobile. Try that.
Sure, let me check.
So yeah, sorry for that, like some unexpected problems. So yeah, we are super happy building monolith. Monolith is the magic word where everything happens in the same place. But it brings some limitations, of course. How to scale? How to communicate with other systems? How can you make the things like more disconnected or more decoupled? We'll talk this word a lot of time here. So at this time that we were building monolith, we had technology like SOAP, XML, RPC, Corba. And why not we implement microservices? Why not we merge a new technology where you can disconnect systems and you can talk with each others? We are starting the coupling here. We are starting to have like not only a monolith, not only a single place that you need to scale and think about all the problems that you have, but we can have like lightweight HTTP APIs, we can have like services talking with each others, but this is not enough yet. And then that brings us to event-driven architecture, the world where everything is disconnected, or should be. So services, instead to talk one to others directly, they are talking to a central nervous system. They are talking to a message bus or even a message brokers or whatever. And I want to highlight here that this doesn't happen because the technology evolved. Of course, technology evolved, but I'm pretty sure that you could build like things in monolith today. But business requirement, world has changed. The way that you communicate, the way that you need to produce data, the way that you need to speed up business, that you need to communicate, it changed. So event-driven architecture is not about technology. This is about business requirement. This is about how world evolved until so far, until today. So, okay, now it's event-driven, amazing, Leandro, but how are event-driven architecture look like? So, before I started showing like architectures and stuff, I see people define event-driven architecture as a message system. So I'm just streaming messages. I see people define event-driven architecture as a pub-sub. So I subscribe to something and I send it to something. So my definition, and probably the definition of many of yours, is event-driven architecture is all about changing states. We change a state, we produce an event, we send it to a central nervous system, that's our message broker, and someone will consume that. We don't have like the direct connection between the client and the server. We have something in the middle can orchestrate that. Okay, Leandro, you talk a lot about that, but let's see in practice how it works. On the top of the event-driven architecture, you have the producers. You have like an order service. Every time that a customer places an order, you invoke the service. Every time that someone starts a payment, you invoke the service. And every time that you change the stock, because you ship a product, you need to change the inventory. But what's these service producers? In the old world, they could do a HTTP call to another service, but not now. Now they are creating messages. They are creating events. Every time that you have like a producer order, you will create an order created. Every time that that payment starts, you have payment processed. And every time that an inventory changes, you have stock updated. You see that the name in the past. So this is a fact. This is a fact that something happening in your system, and they are immutable. But I will cover that in the next slide. Now we have events, and how can I flow this event? How can I flow this data of this event? They are going to like the central nervous system that you can call event stream, channel, topic, bus, depends on your architecture. Today we will cover event stream, but that's true that you can have pub sub and whatever. Now you aggregate messages. Now you are producing different kinds of messages. You are producing order, you are producing email, you are producing inventory, you are producing a lot of things, and they are going to the central system. It's storing, you can replay, you can persist the event there, but it's still missing something. Now I produce, now a customer created an order, I created an event, but I need to do something with this event, right? And then you have like at the bottom, the consumers. You have like some service that subscribed to a topic, subscribed to an event stream, subscribed to a partition, and then you can consume events. But now you can consume different events, and you have different kinds of consumers. You see that you are like splitting the word. We don't have like that straightforward request response that you have in Monolith. We are doing much more with that. I would like to define this one. It's imagine an architecture with events flows to everywhere. Events go to a central bus, and events come out from the central bus. But what is an event, Leandro? What an event would it look like? An event is a signal that something changed in your system. Every time that a customer creates an order, this will create a change in your system. Events occurs in the past that you see. Events are not a command. Events is a fact that something changed. I'm not using create the order because I want to create the order. I use the order created because this is a fact that happened in your system. So that's a characteristic of an event. It should be using like the past tense name. Another thing is events are immutable. So once you produce an event, you can't change that. You can replay that. You can ignore that. You cannot process that because, for any reason, but you can't change that. They are immutable. And it's decreasing coupling. In the previous word of Monolith, so every time that you need to communicate to Microsoft as well, you need to communicate to another service, you need to do a directly call. Now, not now. Now you can put that in a central system, and this central system can be subscribed by many consumers. So, but Leandro, how look like an event? I'm pretty sure that everyone here knows what an event is structured, but just to make sure that you understand. We have here the type that is, I hope it works, let's see. No, too much technology for me. So you have your order created. You have the time that it happened in the past. And you have the data. You don't need to propagate all your data anymore. When you have REST API or GraphQL API, for example, you can send all your domains through the API. Because you never know what's the data that, for example, the consumer or the API will need. But now, it's simple. I just want a francesinha with 2 eggs and fry. That's it. It's simple, right? This is an event, and of course, I'm Portugal. I love francesinha. That's why I put that. For those that doesn't know, you need to try. And that's it. So you can persist only the information that you need for your event. But we need also to cover some characteristics of EDA. We are talking about producers, consumers, events, but we need to cover some characteristics that make EDA an amazing word, at least for me. And the first one is losing coupling. We are now not directly connected to that. You have like producers and you have consumers that doesn't necessarily know about each other. You don't need like to make changes in your consumers and make changes in your producers, for example. You can use schema evolution, schema registry, any other techniques, but in the past days, if you change a class, if you refactor a piece of your code, you probably need to do like in all your monolith. Another thing is real-time processing. So now you are producing events. We can have one consumer to subscribe to that event, or topic, or buzz, or whatever, but you can have 100. You can have 1,000. You can have thousands of micro-consumers consuming the same event. And you can consume different events at the same time. So you are working with real-time processing. The another one is fault tolerance. Now, we'll cover that in the next step, but should the consumers and producers be online at the same time? If what happens if like I produce an event, the event is stored, the event persists in the message bus, but I don't have any consumer to that. What happens? If you have request response, you probably get HTTP for file or 500, but not now. Now you send a message to your central bus, and then it's stored, and when some consumers pin up or some consumers go online, it can consume that message. Another thing is parallel processing. Now you don't need like, in an API you do create the order, process the order, start the payment, and send an email. This is sequential flow. Not now. You can have different events. You can have different producers produce an event, and different consumers consume at the same time. Another thing that it brings of benefit is like heterogeneous integration. Now we know that Rust is saving the world, but Python is building the world, at least my opinion. So you can have producers in Rust, you can have consumers in Python, you can have producers in Java, you can have consumers in TypeScript, in Clipper, whatever you want, in COBOL, for example. That's the beauty of like event-driven architecture when using an event stream, for example. You don't need like to stick or to agree that you just need to use one language. And that's amazing because you have different skills. Not everyone knows one language, not everyone knows another language. This is amazing, the event-driven characteristics. And finally, that my definition is independent evolution. So when you change a producer, when you decide to evolve that producer, when you decide to update the libraries, for example, you not necessarily need to change the consumer. You just need to respect the contract. That's true, but you can do whatever you want to your code. So those characteristics, at least for me, make event-driven reliable, scalable, and adaptable. And adaptable is the word, because we don't need now plan a change that you have like tons of refactoring. That's the characteristics that I want to cover in the event-driven architecture, and I'm going to talk a lot. This is amazing. Leandro, you love that. Most of you love that. But it brings some challenges, right? It's technology. All the technology, you have challenges. And what's challenge that I can cover in the event-driven architecture? Because not everything is flowers and sunshine. It isn't all sunshine and flowers. We have some challenges. Now we have like completely different producers and consumers. And what's bringing? Data consistency. How can I make sure that I have data consistency? How can I make sure when I create an order, this will subtract an item from my inventory? This creates a challenge. Another thing is latency and ordering. And that's nice because 2 days ago, I had to buy some airline tickets in a famous website, and it was like, hey, we are processing your order. And I think, hey, I choose a seat in this airplane, and now someone else will buy another ticket and you choose another seat. So this will respect the order of processment, and you respect the seat that I choose in the airplane, because now it's not strong consistency anymore. This is eventual consistency in some cases. Of course, you can make this strong, but in most of the cases, so ordering is super important and it brings a challenge. Another thing is operational complexity. In the monolith application, you can have like everything in one place. You observe just one server, you observe CPU, you observe memory, you observe one log from Apache, I don't know. And then it's easy, but not now. You have message queues, you have message brokers, you have like different producers, different consumers, how to observe that. We have different tooling. So this is a challenge. I'm not bringing challenges to say this is bad, but this is what it is. You need to be mindful when you choose event-driven architecture, because it's not all like a beautiful word. And finally, and the last one that probably some people make some mistakes, at least I did once. So scalability and costs. This can scale from 0 to billions, trillions, messages, whatever, but it has a cost. So I want to try that, be mindful when you choose an event-driven architecture, because this is amazing. You can like evolve. This is a business requirement, but you need to take care about this challenge when you implement that. And it's bringing me like another idea about, okay, Leandro, we have challenges. You talk about event, you talk about producers and consumers, but what's the communication fundamentals that you have like when you're building event-driven architecture? And I really love to cover like basics, because we can go to the same place. We started the word with this, right? It's never worked, sorry. We start with it synchronous and directly. You have a client that make a call to a server. If the server is up, has memory, is not like overloaded, the load of the service, it's okay, it will work. But what happens if the service is down? It's reply like another HTTP error. How can I scale the server? How can I make my client be aware that I don't have one server, but I have a fleet of servers? I have thousands of servers. That's why someone invented synchronous plus indirectly. We will now have a proxy in the middle. We now have an API gateway, a load balancer, whatever you can have, that client doesn't talk directly to the server, but talk to a proxy in the middle. But it still creates some coupling, because the gateway that in the middle must be aware of servers. And to scale the service, you need to spin up new servers. So it's starting independence, but it still creates some coupling. Oh, not working. Oh, Jesus, my presentation it's broken. Sorry. It's not working. Okay, so we have like asynchronous plays indirectly. That means you have a sender and you have a receiver, but the sender must be aware what the action that the receiver will take. After receive process your message, for example, this will need to send a callback. This will need to send like a post to your service. This creates some independence, but we are not in the best place yet. So final and last, I want to bring, nothing is working here. I want to bring asynchronous plays indirectly. This is the event-driven architecture. So you have now producers that send a message to a message broker, and now you have consumers. So they are independent in the time. They don't need to exist at the same time. You just need to make sure that your broker is up. Of course, you need to start the message. And that's the talk that you covered today. How can I do that? How the techniques to scale, to make this fault tolerance, and all this stuff. But you see that in all these areas here, we are creating some kind of coupling. And I needed to cover this topic, because you needed to be aware that event-driven architecture is amazing, but at some point you need to make a decision. So let me make like a clear statement here, my understanding of coupling. Coupling is not a binary decision. You don't wake up today and you say, okay, I will decouple everything. My system is completely like decoupled. That's not true. At some point, you need to make choice. For example, what about location? So you need to bind a service to a specific IP, it can create a coupling, or you implement a service discovery, for example. What's the trade-off here? How much investment, how much people you need to allocate for that? The second one is format. How can my producers and consumers will communicate? So if I produce in XML and I need to consume in protobuf, this works. So probably I need to make a choice and I need to stick with some format. It's a kind of coupling. You have like how? So you have a temporal coupling that consumers and producers must be online at the same time. So, and finally you have domain like whatever you want. So each dimension here, you must make a decision in your architecture. And I'd like to bring this slide because it's helped me to explain this next one that you call coupling budget. That's amazing. You do event-driven architecture, but you must be mindful about that. You must be mindful that your code with event-driven architecture will become more complex. Your observability tools will become more complex. So what's the trade-off that you need to choose between event-driven architecture and making decisions that you still keep coupling on that? Now that you understand the basics and some advanced topic in event-driven architecture, I will hand over to my colleague Stephen to explain the event-streaming architecture. Oh my God. That's why I just create a joke here.
Okay, now it works. Yeah, so we found out that an event-driven architecture describes how components communicate in a distributed system. We found out that software communicate through events that are immutable, but now we need to cover why should you use a streaming system in an event-driven architecture. And an event stream is basically the technological backbone that you have in order to connect these systems in an event-driven architecture together. And at its core, an event stream just represents all events in your architecture as an ongoing stream of events. And it makes it fault tolerant, it makes it scalable, and it allows you to give producers and consumers the ability to connect to each other and have a decoupled way of communicating. So let's go a little bit deeper and see how a streaming system works. For this talk, we are taking Kafka as an example because it is widely used in the community, but the principles also apply to Kinesis or any other streaming system you can think of. So the basic definition of a streaming system is that it is a continuous stream of events with history retention that allows consumers to independently consume messages out of your streaming platform. And at the core of a streaming platform is the log. A log is just an append-only record of events where producers produce messages and consumers can consume the messages out of. And the data is stored in so-called topics. That's not working. And a topic is just a logical channel where the producer sent the messages to and the consumer subscribe to. And each topic is split into partitions. A partition is just the unit of parallelism within your Kafka environment so that you can make sure that you have enough throughput within your system and the consumers can consume the messages out of it. The ordering, and this is important to know, the ordering is only guaranteed within a partition. So if you have multiple partitions, you will have parallel processing, but likely out of order processing. And one important thing that is different, and we have a talk where we talk also about the difference between a streaming system and messaging systems, like queues, for example. This is not part of our talk today, but here and then I would like to explain a little bit what the difference is because they compete with each other very often in event-driven systems. So in a messaging system like queues, if you consume a message, the message is gone, like it will be deleted from the queue, right? So a message is always dedicated to one specific consumer. And this is fundamentally different to a streaming system where the messages are not deleted when they're consumed, they're deleted based on a retention policy. So this gives consumers the ability to consume the messages out of the streaming system independently, and you can consume multiple messages at the same time. And you see the messages are added to the end of the log, and then the consumers can also consume the messages or the same message at the same time. In a messaging system, you would have to duplicate the messages. You would need some kind of a fan-out mechanism where you use a service like AWS SNS, and then you fan out the messages to multiple consumers. And the ability for the consumers to consume the messages independently is by using an offset. And the offset is just simply a pointer that a consumer uses to track its position within the log. And whenever a consumer consumes a message, it will advance its pointer, so the offset, to a position, to the next position within the log. So now that we covered the fundamentals of a streaming platform and we know how it works under the hood, we need to talk about two very important things: ordering and delivery semantics. And Leo already explained the characteristics of an event-driven architecture, but we need to see how it works within a streaming system. So when we talk about ordering, we need to distinguish between two types of ordering: technical and logical ordering. Technical ordering refers to how messages are physically processed within your streaming platform. So if you have a single partition in your Kafka environment, or let's say a single queue within your environment, technical ordering is pretty straightforward. What arrives first is processed first, right? So whenever the message that arrives first will be processed by the consumer first. If you have two partitions or two queues, you will get parallel processing, but then you have the risk of out-of-order or out-of-sequence processing. And there comes logical ordering. Logical ordering refers to the ordering based on the business meaning of your events. So you will order your events based on some kind of an identifier that you use, let's say the user ID, for example. And then you need to make sure that you reconstruct the logical ordering on the consumer end. This is easy to achieve on a partition level because, as we found out, ordering is preserved on a partition level, but not on multiple partitions. So, as you see here, within logical, when you want to achieve logical ordering, we see that the events A1 to A3 and B1 to B3, they happen in specific moments in time. And what we want to achieve is for the specific logical group of B1 to B3 and A1 to A3, we want to maintain the logical ordering within these groups. So what we need to do is, on the consumer end, we need to make sure that these events will be reconstructed. So we need two identifiers here. One is like a logical grouping identifier, like the user ID, for example. So for a specific user, we want to have all the orders in order. And the other thing is a sequence identifier. So some kind, and Leo made the example like that you have a timestamp within your event, and based on the timestamp, you can reconstruct the order based on the user ID. So within a streaming system, as I said, technical ordering is preserved on a partition level. You will send the events to a specific partition based on a partition key. And you have to make sure and think about how you want to construct the partition key to make sure that the events land on the right partition. If you want to have logical ordering, then you need some kind of a stream processor, and you can use Apache Flink for this, or Kafka Streams, or whatever you're familiar with. And then you can use this stream processor to reconstruct the logical ordering on the consumer end. It is worth mentioning that if you need to preserve the ordering, this will always come with the trade-off of lower throughput. Because if you have a single partition, you, of course, have not parallel processing. And if you want to reconstruct the logical ordering on the consumer end, and you use Flink, or it doesn't matter what you use, it will use some kind of a windowing technique underneath to make sure that it reconstructs, and a windowing technique is nothing else than a buffer. So it will reconstruct the logical ordering on the consumer end. This will also come at the cost of throughput. So let's jump to delivery semantics, because this is also something important you have to consider when you build your event-driven architecture. We need to distinguish between three types of delivery semantics. One is at most once delivery. At most once delivery follows a fire and forget approach, where a producer sends messages into an event bus, and the event bus will fan out the messages to one or multiple consumers. The advantage that you have with the at most once delivery is that you have very high throughput, because you don't have the overhead of sending acknowledgement messages to the event bus from the consumer, or the event bus doesn't have to acknowledge the message back to the producer that it received the message. The downside is, of course, it's not very reliable. So you have the risk of losing messages within your event bus. For example, if the consumer processes the message or tries to process it and fails, so the event bus, the message is lost then. So the idea behind this is that you use at most once delivery if you have very high throughput requirements and non-critical data, like high telemetry or metrics. The second one is at least once delivery. And at least once delivery says that the messages are not lost, but may be delivered multiple times to the consumer. So the producer sends messages to your message broker or your streaming system and receives an explicit acknowledgement that the message was delivered. And the same goes also for the consumer. And the messages are then deleted only if the message broker received an acknowledgement from the consumer that the message was processed. And here you need to make sure that you can handle duplicates within your system. And now the most important thing, and also the the hardest thing to achieve is exactly once. So exactly once delivery, exactly once delivery is something that is already proven that is impossible to achieve in a distributed system. So it says that the message is delivered exactly once. This is something we cannot achieve. But what we can achieve is exactly once semantics. And at its core, it means that a message is delivered at least once, and that the message is produced in a way that duplicates don't matter. So in other words, we need an idempotent consumer. This sounds simple, but in distributed systems, it's one of the hardest things to achieve. So in messaging systems, you would use some kind of a deduplication ID that makes sure that the messages that come into your systems are delivered only once by the producer. And then you need some kind of a message ID that uniquely identifies your messages within your system. And now you need some kind of an external data store, like some kind of a database, that stores these message IDs and tracks whenever a consumer acknowledges that it processed the message, it needs to verify, okay, did I already process the message? So this will happen based on the message ID in the data store. And now you need some kind of database, atomic database transactions, right? So you need to tightly couple the database transactions with the acknowledgement of consuming the messages. I say this because in a streaming system like Kafka, Kafka goes way beyond or has much more native support for exactly once semantics compared to a queuing system like SQS. Because, and I just want to, we just touch on this because we can, I think, talk 3 hours about exactly once semantics in Kafka, but Kafka delivers you, for example, producer idempotency. It's just a feature that you can enable within Kafka that makes sure that the messages that the producer produces is not creating duplicates within your Kafka environment. Secondly, you have Kafka transactions. And Kafka transactions gives you 2 atomic guarantees. On the one side, it guarantees you that the producer who produces a bunch of messages to one or multiple partitions or topics bundles these message production in one atomic operation. So either all of these messages will be delivered to Kafka, or none of them will be. And the second atomic guarantee that Kafka gives you is on the consumer end, that a consumer takes the message out of Kafka, creates an output, creates or pushes the output to a second topic, and commits the offset back to Kafka. And all of these 3 operations will be also one atomic operation. And all of these things give you the ability to have exactly once semantics much more easier in Kafka compared to messaging systems. And then if you want to use a stream processor like Flink, these stream processing systems give you also the ability to have exactly once semantic support built in the framework itself. So this is also something that you don't need to take care of within your streaming system. And the last thing is that it's worth noting that even though Kafka gives you all these capabilities, you still need the consumer idempotency if you go beyond your stream processing, so beyond your streaming system. Because as soon as your consumer is writing to a downstream application or some kind of a database, you still need the consumer idempotency because otherwise your idempotency breaks at the final write of your system. And the last topic before we jump into our example, our real-world example, is scalability. So how does a streaming system scale? So we take here MSK, so this is the managed service from AWS for you, for Kafka in your cloud environment. And a Kafka cluster consists of a control plane, of 1 or more brokers within your system, and attached storage. We use EBS volumes for this. And optionally, a tiered storage for offloading data to save costs, because it's very expensive to store data inside a Kafka cluster. And now let's say we want to increase the throughput. We have more producers producing messages into our cluster, and we have more consumers consuming the messages. So that means that we, at some point, will increase the number of partitions to have the parallel processing in place. And then we need to make sure that we have enough storage within our cluster. So we increase the storage. And then next we need to decide whether we need to increase our compute power, because this, of course, with increased traffic, we hit maybe CPU limits or memory limits. And then we need to make a decision. Do we want to scale horizontally or do we want to scale vertically? Scaling vertically means we increase the instance size. So we keep a lower number of brokers, but we increase the CPU and memory power of the respective instance. The advantage that you, of course, have is that you have much faster upgrading and patching time because you have a lower number of brokers. The downside is you have a much higher blast radius. So if one broker goes down, the remaining brokers have to handle the load of the traffic that comes into your cluster. The other idea or the other possibility that you have is horizontal scaling. So we increase the number of our brokers inside our cluster. And here we have the advantage, of course, that we have a lower blast radius, but we have much longer upgrading times because we have a higher number that we need to upgrade here. And you see that it is not very easy to manage a Kafka environment and to handle the scalability and have it production ready. And for this, hyperscalers like AWS offer customers different cluster types to make sure that it aligns with your requirements and what you actually need to run a Kafka environment in production. And for this, like the first possibility that you have is using a standard provision broker. And the standard provision broker takes care of the control plane for you. So you don't have to take care of managing your Zookeeper or in the future already KREF environment. So you have maximum configuration options here, but don't need to take care of the control plane. If you, and this is the second option and second cluster type that you can use, Express Broker, if you don't want to take care of the storage management, so increasing or decreasing your storage or enabling tiered storage and so on, this will be, this is your cluster type, so that you can also benefit from much higher throughput and performance because AWS like optimizes the storage and the connection between the storage and the compute. And lastly, there are also serverless clusters that give you the ability to, well, that everything is managed for you. So there are still servers, of course, but you only have to make sure that your producers and your consumers can connect to the serverless cluster. But there's always a trade-off. The trade-off is that you have much less configuration options within the serverless cluster because most of it is managed by AWS for you. And with that, I will again hand over to you.
I hope it's working now. Yeah, but before I jump into the real-world example, let's see some common patterns that you have when implementing EDA. And they are like just not theoretical stuff, but they are concrete examples of architecture that you can adopt when using Kafka. So let's take a look on this parameter. The first one is communication patterns. You have like pub-sub. You publish to something, you subscribe to something, and then it's happening. It's simple, but this is powerful. The second, you have like data replication. Like Kafka keeps like a durable log for you, and you can replicate that. The other one that probably some of you are using, it's CEDA pipelines. When you can send an event, you can transform an event, and you can enrich this event. And then you can propagate that. We are going up. You see that we are increasing the complexity. And now you have the patterns recognition. This is widely used in fraud detection, for example. Imagine that like make an order in Portugal and Brazil and Australia using the same credit card at the same time. So there is something wrong happening here. So Kafka can help you to aggregate those signals. That's like everything is a signal. You can aggregate those signals and you can detect the patterns on that. You can see, okay, there is something wrong here. Let's investigate that. And on the top of the parameter, you have like the famous CQRS that you read and you write to different models. Not everyone needed to go to the top, but everyone needed to start from the bottom. and you can use Kafka to help you in this journey. You can easily start from like a pub sub, and depends on your business requirement, it depends how much your business are growing, you can evolve it to the next layers of this pyramid. But again, let me touch quickly in the CQRS patterns here. You see here, like if this is architecture, you have like a client that sends comments, like write or, update, delete, whatever, and you send a query. They flow through different patterns. They flow through different places. So you have the comment handler and you have the query handler. And you read that, you write that in a different place. So why I'm bringing that? Because CQRS enables you to unlock flexibility. CQRS patterns help you to achieve scalability and be more flexible. But again, I'm talking a lot. Let's see a real-world example how to use this pattern. So imagine an e-commerce platform. We have like some business requirement. We need to have multiple services. Because e-commerce, you have order, shipping, payment, email, whatever you have. You need to deal with high volume transactions. Because in a normal day, you expect it to sell 1 billion euros per day. That's amazing. So I don't know if you read it, but it is a good topic. You read the AWS Prime Day. You see how this is scale like event-driven architecture in super high numbers. This is a public web post, you can search that. And another one, you need to deal with real-time data. So that's the business requirement, but it's simple to implement that. You have some challenges. You need to scale quickly, because now we have like at 8 a.m., people are waking up and want to buy and to spend money. So you need to scale quickly, because it can go from 1 customer to 1,000 customers. You need to have data consistent. Do you remember my example about like booking a flight? How can you keep data consistent? A lot of people choosing the same city, the same airplane city. So you have this challenge. You need to high load spikes. So imagine Black Friday. Jesus, this go crazy. I work in e-commerce with Black Friday, and it's Jesus. And you need to deal with third-party integration. So probably you are building your commerce, but you are not the owner of the gateway of payment. So how can you make sure that this integration won't affect your business, your requirements? So I hand over again to my friend to explain some requirements and how to implement that in architecture.
Yeah, so the idea that we had, and this is really a conversation we had with the customer around their requirements and how we want to implement the CQRS pattern. So we will use DynamoDB as a NoSQL database, and please, if you're not familiar with the AWS services, that's not a problem. It's more about, the idea is more explaining how like Kafka can help you with this, rather than understanding why we chose a NoSQL database over a SQL database and so on. So the idea is that we had some fixed parts that we talked with the customer about, and one is that we have a NoSQL database with a single table design where your consumers or your customers create events based on your e-commerce platform, and these events will be stored in the DynamoDB. And then you have an event sourcing, so you create a CDC pipeline that creates the events or streams the events out of DynamoDB. And now you have around 50 to 100 consumers of your Kafka environment that need to consume these messages. And then, because we have CQRS, we need some kind of a read model updater who reads the messages out of Kafka in order across all partitions, and then sends these events to a SQL database for your read model updates. And we have 3 key requirements from the customer. One is performance. So we said that we need under 100 milliseconds of latency. The second one is scalability. So up to 50 or more than 50 consumers. At the beginning, it's like 10 or 15, and then it can go up to 100, 200 or more. And the last thing is that we need guaranteed message ordering for our read model updates to stream them to our SQL database. So we have some fixed parts. This is the DynamoDB, our NoSQL database. We have RDS Aurora as our SQL database. And as I said, it doesn't matter how these systems work under the hood. And And then the service on the left side is just like the customer creating events, like placing orders in our e-commerce platform. And then this will be streamed to or sent to DynamoDB. And then DynamoDB has a CDC stream built in. It's called DynamoDB Streams. So it streams all the events, everything that happened inside our e-commerce platform. It creates a continuous stream of all the events that happened inside your DynamoDB. And then we need to think, how can we stream those changes from the DynamoDB stream to multiple consumers and have guaranteed message ordering for our read model updates that will be sent to the Aurora database. And one idea, and this is one solution, there are multiple ones, and in our other talk about messaging and streaming, we showed the customer also how this can be solved using messaging systems like a queue, an event bus, and a topic, like a publish subscribe, like SNS. So there is always like 1,000 ways to roam, how you can achieve this. One way would be that you can use one like compute instance. We use Apache Flink for this, like a stream processor, who streams the changes from your DynamoDB. And then you can optionally transform the events, you can filter the events, map the events, everything that the stream processor does. And then you stream those messages and events and send them to Kafka. And then Kafka gives you the ability to connect to your consumers and also scale out in the future to hundreds or thousands of consumers that you have. And then for our read model updates, you can use another Flink job that connects to your Kafka environment, and Flink is capable as a stream processor to stream messages out of multiple partitions in order using these windowing techniques we talked about earlier. And now we fulfill all the requirements that there are. Another option that you could use maybe is using a Lambda function. Why? Because maybe your team is not familiar with Flink, or you're not familiar with running Flink in production, so you don't want to like use a stream processor, basically. So what you can do is you can use a Lambda function, what is basically just a compute instance where you can run code snippets on. But we have one problem here. And the one thing is that Lambda is not capable of streaming messages or events from multiple partitions in order. So now we don't fulfill our requirement of having guaranteed message ordering for our read model updates to our RDS database. So this is something that doesn't work. But what does work is that you could use the Lambda function and connect it directly to your CDC stream. And the other Lambda function connects from the CDC stream to Kafka, sends the events to it based on the partition key and to multiple partitions. And then your downstream consumers can consume the messages from the partitions. So now you have also, you reduce the latency for your read model updates because you connect your Lambda function directly to your CDC stream. So this would be a working solution here. As I said, we also talked with the customer about other options using messaging systems, but out of time constraints, we left this solution out here. And now we are at the end of the talk. The only thing that I want to mention are some key takeaways that we talked about. One thing is that event-driven architecture is something that evolved over time. And please take into consideration, like, there's always a trade-off. Like, there's no silver bullet that solves all of your problems here. A streaming system comes with challenges. A streaming system gives you a lot of benefits. But we see a lot of people in the community that, like, praise that Kafka is the solution that brings you all the benefits and no disadvantages, but you always have to make a distinction, when does it make sense compared to other services that we have out there. And the beauty of like cloud environments or the technology in general is that you can choose whatever service or framework fits best to your needs. And this brings me to the second part, is that decoupling always comes at its cost. You need to make sure where you want to couple, where you want to decouple your system, and in which dimensions. And lastly, the event streaming is something that can power your event-driven architecture if you want to use it. But as I said, it comes with challenges of much more management overhead compared, let's say, if you want to use a queue or an event bus. So this is something you have to be aware of. What we didn't talk, for example, also in the real-world example, is we didn't talk about other things that are very important that you need to think about is cost efficiency. We haven't touched on this here. Or the tech skills within your team, like how familiar are they with running Kafka in production. So these are things we haven't touched on because just out of time constraints, but just keep in mind that this were like a few dimensions, some food for thought that you need to take into consideration when designing your event-driven architecture.
Yep.
And maybe my last ask is, give us a rating maybe, please, we want to improve here also the content of the talk and whether it was beneficial to you. So thank you very much.
Thank you, sir. Yeah. Hello.
Yeah. Also, if you got questions,
Hello.
we are around here. We
Yeah.
can also make, I don't know whether we have time for this,
Hello.
but we are around here for Q&A or see you later at lunch.
Thank you so much.